Okay, good morning students. So now moving on to the discussion that we were having last class, that is design of advanced current mirrors. So what we are looking at is how to design a current mirror which is having a very high impedance and which is requiring a very low headroom. That means I do not require too much of voltage to drive that circuitry only, because normally current source is either at the bottom or at the top. So it is always coming in between 0 to VD. So if it is consuming too much of a headroom, voltage requirement is too much, then the voltage range available for amplifier to work reduces, which affects its swing, which I do not want. So I want why? Because for me, biasing is not taking part in dynamic operation. It is only providing a bias. So I need to design the circuitry such that it takes very less voltage requirement. So that is what we are looking at, and in this quest we were looking at the ways, and we tried modifying the cascode and Wilson. So last time what we did was we took cascode, we did its analysis, we took Wilson current mirror, did its analysis, and then we tried to modify it. Then we tried to modify it so that I can reduce the voltage headroom requirement and I can increase the resistance. When I increase the resistance, that means any change in voltage which is happening, because R is V by I. So if V is changing by delta, if I is not changing, then R tends to infinity. Then R will tend to infinity. That is what I want, that there is some negative feedback happening within the circuitry such that it does not, or it wants my I to roll back to its initial value. So either it roll backs fully or it roll backs such that the difference change, increment or decrement is very small, such that delta V upon delta I, which is nothing but your R out of the current mirror, so delta I will be small. So R out increases. So this is what will happen when we include negative feedback in our circuitry. As I showed you in both the circuits, cascode as well as Wilson, we have a negative feedback circuit coming up, which allows it to make its current to roll back. Hence R out increases. So we used the principle of gain boosting there. Cascoding and gain boosting. Two things are done. Cascoding and gain boosting. So look at the slide. So this is what, now this is a gain boosting that I am doing. It is a gain boosting, it is an amplifier. Whereas this is my common source amplifier, and this is just to propagate change at this node to this node. It is just to propagate the node from here, node voltage or perturbation or variation from here to here. And once the perturbation reaches here, this common source amplifier produces minus gain times the input. So this gate reduces. So VGS reduces. So any increment here causes a decrement at this load, at this node. That is why causing the VGS to reduce. So I will come back. I will roll back. I will come down. This is the principle. We are using gain boosting. And this is increasing your R out to how much value? Last time we did the derivation. Yes, Manasa, what was the value?
GM square RO cube by 2.
Yes. So it increases from GM RO square to GM square RO cube by 2. It increases to that value. And the voltage headroom requirement is very less. Only 1 V overdrive for Q2 and 1 V overdrive for Q1. That is only 2 overdrives voltages. Only 2 V overdrive. That is, if my V overdrive is 0.2, I can have circuitry working within 0.4. Only requirement is 0.4 volts. I do not need more than that. And this is where you have a connection. Okay. So you can see it's a low voltage cascode. So this node comes to VGS minus VT 1 overdrive, and this node also comes to 1 V overdrive. So there is no lambda mismatch. There is no lambda mismatch between IREF and I bias. There is no lambda mismatch. And to create this voltage 1 VGS plus 1V overdrive, same voltage I need here, so I simply replicate this circuitry over here. Or you may not replicate, you can go for another solution that I showed you in the last class. But then we try to have a matching, so we try to have the same circuitry for the reference as well as for the biasing arm. It is good to have the same circuit. But nobody says that you cannot go for other solution here, because this is in any way is not for this arm. Its only purpose is to create this voltage so that you can bias Q5. Its only purpose is this. But this is critical. Why? Because this is giving you gain boosting. Because here, a variation here, because of say node fluctuating, because of amplification process. So this node will also fluctuate. So this node will also fluctuate. So a minus gain times fluctuation appears here, which causes a negative feedback. If the reverse happens, suppose perturbation is negative, then your gate voltage increases, so VGS increases, current increases. So both ways it works. Whether you have a negative change or you have a positive change. Whether you have an increment or a decrement. So in both ways it changes. So this is one advanced current mirror circuitry where you are getting a very low voltage requirement and you are getting a very high RI. And this is particularly useful to an op-amp to generate ISS where you are going for single output, because then your P node, VP node, it never comes to 0, AC ground. It never comes. So I want a very high RSS current mirror over there. So I can use this structure. So wherever your P node is not coming to AC ground, I can make use of a high RSS. I should make use of a high RSS current mirror. So this circuitry can work as a current mirror circuit over there. Clear? Is this clear? So now just one thing before we stop our discussion on this, that is, if there is a mismatch. So I will do this mismatch analysis only for a basic current mirror, so that you understand the concept. So what if there is a mismatch? Because two transistors, though we assume matching, they may not be perfectly matched. They may have some deviations. So we may have a mismatch in VT. We may have a mismatch in W by L. Okay. So accordingly, if the things are varying, so how does it impact your current transfer ratio? Because current transfer ratio is something I expect I bias by I reference must be 1 according to me. But if it is not, then can I calculate how much different my I bias will be in comparison to I? Can I compute this difference? So I should have some expression with me. I should be able to derive some expression using which I can compute how much difference I am going to get if there is a mismatch. Because mismatch is inevitable. You cannot reduce it to 0. Though you can minimize it, but you cannot make it 0. Okay. So if there is a mismatch, now look here. So normally if this is my biasing arm, okay, and this is your reference arm. I am not showing the upper portion. Okay. I am not showing the upper, only the basic current mirror. So this would be connected to amplifier here, and this would be connected to the reference current source. Okay. So I can write the equation as mu n C ox W by L VGS minus VT whole square. Okay. So let me say mu n W by L is beta. So it is M2, so beta 2. And this is M1, so beta 1. And VGS minus VT whole square. If you have a lambda coming in, so you will add one more term, 1 plus lambda VDS2. And this would be 1 plus lambda VDS1. And that VDS1 will be same as VGS1. You need to add one more term. Clear? Go campus. So now, if I say there is a variation in W by L or Tox, whatever we change, beta will change. Whether your Tx will change or your W by L ratio will change, this beta will change. So let me say there is a change in beta. So difference delta is beta 2 minus beta 1. Okay. Second effect can come from VT variations. So there is a change in VT. Vt is also different. Threshold voltage. This is dependent on implantation. Implantation happens because of diffusion or ion implantation process. So this can also vary. So suppose change in Vt is given by Vt2 minus Vt1. Now I take an average value which will give me the nominal value for beta as the average value. So I compute two quantities. One is the difference. One is the average or nominal. Which is nothing but the average of the two. So this would be beta 1 plus beta 2 by 2. And this would be Vt1 plus Vt2 by 2. I compute two different quantities. I know my beta 1 is not same as beta 2. I know my Vt1 is not same as Vt2. So now using these equations, I can write my beta 1 in terms of beta only. Similarly, I can write my Vt1 in terms of Vt only. Similarly, I can write beta 2 in terms of beta. I can write Vt2 in terms of Vt. I need to make use of these four equations to get the expressions for beta 1, beta 2, Vt1, Vt2. Okay. So once we have got these equations with us, now what we do is that we write the current transfer ratio once again. IO by I1 or ID2 by ID1 ratio once again. So when I write, it would be again, remember the beta 1? Beta 1 is written as beta plus delta beta by 2. Beta 2 is beta minus delta beta by 2. Clear? Then VGS minus VT1. VT1 is written as VT minus delta VT by 2 whole square. Then VGS minus VT2. VT2 is written as VT plus delta VT by 2 whole square. It's very obvious. VT1 is, I'm taking VT1 to be less and VT2 to be more, and VT is somewhere in between. It's an average of the two. So one component will be plus delta Vt by 2, other component will be minus delta Vt by 2. So simple. So I rewrite this whole expression and then I simplify. And then I simplify this equation. So what I do is that from this equation I take beta outside, and from this expression I take VGS minus VT whole square outside. From this whole equation you take beta times VGS minus VT whole square times outside. So when you take this, similarly I do from here. And remember that moment you take beta VGS minus VT whole square, it is occurring in the numerator as well as in the, so they cancel out. And rest what is left is this. It is just a simplification I am doing. I hope everybody is able to visualize. Yes, Mr.
Yes, ma'am.
So we are simply, now this is a simplification process. A very simple simplification process. Okay, so we have got 1 plus delta beta by 2 beta, 1 minus delta Vt by 2 VGS minus Vt whole square. So if I now take, this will come minus 1 up with the minus 1. I can take this whole denominator up with the power minus 1 and I can use, now remember I can use binomial expansion. Why? Because the second term, this term is delta beta upon 2 beta. Delta beta is a variation and variation is not going to be large because I would be taking proper care in layouts. I am going to use common centroid geometries and whatnot. So delta beta is going to be small. So that means second term would be much small in comparison to 1. I can very well use binomial expansion. And then discard higher order terms. I can use binomial expansion. This is what is done. So for this term, which is to the power minus 1 when taken to numerator, you expand it binomially. And then discard the higher order terms of delta beta. So delta beta square, delta beta cube, all these terms are discarded. So we are retaining only delta beta term. We are retaining only the term containing delta beta. Similarly, for this, same thing I am doing for this. When this is taken up, this whole thing will be to the power minus 1. Again I expand this term binomially and then retain only the delta Vt term. So I get only delta Vt term. So this plus will become minus. And then the whole square comes here. So 2 terms multiplying to the power 2. And these 2 terms multiplying together. Now when you multiply them, you again get 1. What will you get? The term 1, the term delta beta, one more term the delta beta, and another term will be delta beta square. Since we are discarding higher orders of delta beta, again you discard delta beta square term. So what is left is only 1 plus 2 delta beta by 2 beta. Now please visualize the mathematics in your mind. I can do in a piece of paper, but I think this is something that is very trivial. Am I correct, Kirti?
Yes, ma'am.
Okay. So when you multiply and then we discard delta beta square term, this is what we are left with. And then similarly you multiply these two together, discard higher order terms, and then multiply whatever you are getting here and whatever you are getting here together. You have to do full simplification. Again the 2 delta beta terms you are removing, delta beta Vt term you will remove. A product of delta beta into delta Vt you will discard. Okay, so what is left is only this. Finally, so now this is what is giving you the effect of mismatch on current transfer ratio. This is what, because now you can see, I can find out a deviation which is dependent on mismatch in beta and which is dependent on mismatch in delta beta. So if I say that mismatch is say 5%, okay, mismatch is 5%, that is delta beta by beta value is 5%. So I simply put 5% value here, and for this is, suppose it is given as 10%, so I put 10% here. So mismatch between IU and I1 will be the one value plus minus 25%. That means your IREF can deviate, sorry, I bias can deviate from IREF by plus minus 25%. So if your I bias is say 50 microampere, compute 25% of it and then add or subtract. This much variation you can obtain. So this is, remember, this is the worst case. This is the worst case where I am assuming that Vt is also causing current to decrease and beta is also causing the current to decrease. So total effect is a net decrease. So that will cause the current to decrease largely, majorly, in a major way. So we are assuming that all parameters are so changing, beta, Vt, that they are causing a worst case deviation. It may not happen because your beta may be increasing and Vt may be decreasing. So this is giving you the worst case deviation. So maximum deviation that you can obtain, you can compute by using this relation. So this is known as a mismatch analysis. So I know that even if there is a huge, you can say, care I take in the schematic, process variations, which is something I cannot have a zero control, a full control, 100% control, I am going to get a variation. So we say let process variations only have a say on mismatch. So why should lambda have a mismatch? So that is why we want to make the two VDS same. That's the reason in my design I want to make the two drain source potential same. So look very carefully. That is why I am so concerned about this VGS minus VT, because this is a VDS, and this VGS minus VT, which is this VDS. They need to be same. Otherwise, if these two are having different values, they are the basic current mirror pair. They are making the basic current mirror pair. If these are different, definitely these are going to be different. They will be different. So at least the process variations I am not able to have 100% control. Design I should do perfect. Then you can say that we are having so many biasing arms. Yes, I agree. That means I am using too much of a power. I am consuming too much of a power. But then I am gaining on my efficiency. Now my current mirror is much more efficient then. So there is a trade-off. So I am adding too many, you can say, reference arms. So these reference arms you create only once and then simply mirror. It's not difficult to create a 7 times IREF, 4 times IREF. You can easily replicate by using a current mirror. You need to create only once. So that is not a trouble. But then certainly more number of independent arms are there, more will be the power consumption. So more hardware you put in, more complicated you make your circuitry, but efficiency will be large. Clear? Any question here before I stop this topic? Any query, Srinivas?
No, ma'am.
Salahuddin?
Ma'am.
Nirmal? Manish? All you have got it. So designing is all about W by L. Finding this thing you know. But you should only understand how to design the circuitry, because circuit is, once you know the topology, you can always calculate the W by Ls. Okay? So once I know this, I can use this concept now in implementing my ISS or in implementing my load. Differential pair active load. Remember, I can use this structure as a load also. But then this is there when you use it as a load. Okay, it will give you a high RSS. But this is not for setting the ISS. Remember, when you are using it as a load, its purpose of setting the ISS is not there. Only when you use it for the biasing purpose, then this purpose is met. Remember that. You can use it either as a load or as a biasing circuitry. But how do you use it? Accordingly, either ISS will be critical to you, or it may not be in any way making you to set ISS. But then it will give you a very high load and will take a very low voltage requirement. So that swing is increasing, but gain is also increasing, because gain is GMR out and R out is very large. Load is very large. So you can use the current mirror in two ways, either as a biasing or as a load circuit. Understood? Clear? So now, I have got 2-3 things. That is, current mirror we have finished. And now we move on to within something which is related to current mirror is the reference. Every time I am showing you an IREF with a current symbol. Every time. So we are designing it like this. IREF shown here. A current mirror pair. And this is my amplifier. This is my VDD. Every time I am showing an IREF over here. Initially we used to show the circuitry with a resistor. Initially we used to show it with a resistor. Gradually I started changing this resistor to IREF. Okay, why this was done? Because just to show you the concept of IREF. That IREF means generating a current in this arm. How to generate this current? Very simple. VDD minus VGS divided by R will give you the current. So current is known. VGS you choose, accordingly set the W by L. It's very easy. So designing a reference arm is very easy, but we do not use resistance. We do not use, because resistance will not ensure a constant IREF. Why? Because resistance changes with temperature. At the same time, if VDD fluctuates, the current through R will change. So it is prone to both VDD as well as temperature fluctuations. I should not use R, because when I say I reference, this means a kind of a standard current. or a standard voltage. What do you mean by a standard? Means something which is not changing. This is what I mean by a standard circuit or a standard parameter. That is, it should not change. It is immune to factors, varying factors. What are the varying factors here? VDD fluctuations and temperature fluctuations. So if I use an R here, I cannot guarantee the constancy of IREF. VDD fluctuates, IREF fluctuates. And I bias is a mirror of I reference. So if I reference is shifting, I bias will shift. If I bias will shift, my Q point will shift. And on my Q point depends all my small signal parameters, GM, RO, GMB. They depend on the bias current. So if my bias current is changing, my small signal parameters are changing. And if my small signal parameters are changing, my gain will change. So that means I cannot guarantee to my customer that to take this circuitry or amplifier, you will get a gain of 10. No. I will say, okay, you will get a gain between 9 and 11. So there is a range. That means reliability is not 100%. You cannot say with guarantee. You cannot say with guarantee. So now, if a user does not want a gain of 9, he wants a gain of 10 every time. What should he do? He will ask the designer to design a circuitry which will give him a gain of 10 only, nothing else. So how to guarantee that I bias will not change? That's the only way he can design. Guarantee that I bias will not change. So this is to be done by making IREF constant. IREF has to be constant. Whatever happens in VDD, whatever happens to temperature, I reference should not change. That is why this current is called as a reference current. Means something like a standard, a reference. When you take a reference, I'm comparing myself with you because you are not changing. I may deviate, but you are not deviating. So how much deviation is happening, I can easily compute because I have a reliability that you will not change. So how much deviation is happening, I just look at my position and I compare it with you. I can get the deviation. If you are also changing, I am also changing, the deviation I cannot find out. I do not know whether earlier it was less or now it is less because you are also changing this way, that way, I am also changing this way, that way. I cannot know. So something which does not change, which remains a reference, which remains something like a standard thing. Okay, something like the standards that we have for NKS unit. We have 1 meter, we have 1 kilogram. How do you measure how much is 1 kilogram? So we have a bar of some metal which is kept in, say, somewhere in Russia at particular temperature. If you always weigh that bar, maybe of a gold or something else, it will always be taken as a standard 1 kg. All the other references in the world of mass, they are compared with that weight. Whether they are more than that, it is more than 1 kg or less than 1. Something like that, standard units. Similarly, the standard here, we need to design a standard reference circuit. So how to design a circuitry such that this IREF will be constant. So this IREF, though I am showing it with a current symbol, it is actually an entire circuit. It is actually a complete circuit. It is not a symbol. Though we were representing it with a symbol. Why representing it with a symbol? That is a current source. I could have also used a voltage source. So I can generate either IREF or I can generate or VREF. Doesn't matter. Once you generate IREF, you can convert it to a voltage. Once you generate VREF, you can convert it to I. But you can generate both IREF as well as VREF. There are ways in which we can do that. So either generate a reference voltage or generate a reference current. Clear? So once we have the references. Now we know the concept of references. Now I know the concept of references. So I know what is to be done. I know my objective. What I want. What is that? But that is I want. So I want a reference where if Iref it is always constant. And if it is a Vref it is always constant. Here you may plot VDD or you may put temperature. On this axis. No change. It should not change. This is what is my aim. So now, how to know if I design a circuitry? How to know how good is my circuit? We need to characterize. We need to know whether it is a you have designed, I have designed, whose circuit is best. How do we know? So just for amplify, we look at gain bandwidth, we look at the gain, we look at the swing, we compare. Similarly, here also we should have some characterizing parameter. Looking at which I can say, okay, yours is better than mine. So we call this parameter as stability. Oh, sorry, sensitivity. Sensitivity parameter. This is called as a sensitivity parameter. So what does sensitivity mean? We define it as a parameter S. So change in, now this is a sensitivity of Vref or Iref, whatever it is, with respect to a certain parameter, say temperature or VDD. We define a sensitivity parameter. So S of Vref with respect to X. Sensitivity of Vref with respect to X. So I can put it as sensitivity of Vref with respect to temperature. Sensitivity of Vref with respect to VDD. Similarly, sensitivity of Iref, accordingly you will change your expression. So in what's the definition? How do you define? It is defined as a ratio of, understand? It is defined as a ratio of percentage change in reference with respect to percentage change in the, say, VDD. So if VDD is changing by 10%, how much variation is coming in Vref? If Vref is also changing by 10%, that means the sensitivity is 1. Do I want my Vref to change? No. So ideally my Vref should not change. So percentage variation in Vref must be 0. My VDD may be changing by 10%, but Vref should not change. So my ideal value for sensitivity is 0. And maximum value of sensitivity can be 1. Because if VDD is changing by 10%, Vref is also changing by 10%. What is I am doing for? I have designed a very bad circuitry. My circuit should be designed in such a fashion that even if VDD changes, it suppresses those variations, does not allow, should not allow those variations to propagate to Vref. It should not allow. Then I'm doing a good design. Then I'm doing a good design. Otherwise, I'm doing a very bad design. So sensitivity changes by between 0 to 1. Its good ideal value is 0 and worst case value or very bad value, maximum value is 1. So if your value is coming out to be 1, it's a very bad design. And if your value is coming out to be 0, it's a very good design, ideal design. So though you may not get 0, you are still able to make your sensitivity close to 0. It can be close to 0. So now I know I have to design a circuitry whose sensitivity is close to 0. Clear? So let us see in how many ways. Every time I look at various ways of generating Iref or Vref, I keep on computing the sensitivity. The moment I get a sensitivity less than 1, I would be delighted. If I am getting a sensitivity of 1, I would be depressed. No. So I will keep on finding out ways which are more, for which I will get a sensitivity of 0, which are desirable to me. So let us look at various ways in which you can generate a reference, maybe a voltage or a current. Currently I am not distinguishing between the two. So if you have resistor ladder. I can generate a VREF using a resistor ladder. So now if you take a VDD and I use a resistor ladder, RA, RB, RC, I can make my V2 as a reference, or I can make V1 as a reference. In whatever way you do it, V2 would be given by this expression. And okay, if V2 is my reference, suppose V2 is given by this expression. To compute its sensitivity, I use the definition of sensitivity. What's the definition of sensitivity? Percentage variation in VREF with respect to percentage variation in VDD, or if you simplify, this VDD will go up, VREF will come down. Okay, you will get this as simply VDD by VREF into differentiation of VREF with respect to VDD. So VDD by VREF, anyway I know I only need to compute differential of VREF with respect to VDD. I use this definition. So I have an expression for VREF here. The V2 is my V reference. V2 is my V reference. I take its differentiation with respect to VDD and I substitute it in my sensitivity expression. When I do that, it is VDD by V2 into this differentiation which I substitute, differentiate this. Differentiate whatever comes, you substitute it here. This is what you get. We are assuming only VDD is fluctuating, not temperature, so this will be a constant term. It will not changing. But you look here. If VDD is changing by 10%, this is the sensitivity of VREF with respect to VDD. This is the other way around. VREF come here, VDD should come here. Just be careful. So sensitivity would again be changing by giving you a value of 1. It will give you a value. You will not get it less than 1. If VDD directly is coming over there. Compute this value, it will come out to be 1. It's a very bad design. So I should not use resistor ladder to generate a VREF. Got it? This, you can say it is coming out to be 1 because VDD by V2. What is VDD by V2? It would be RC plus RB plus RA by RC. Substitute it here, everything will cancel out. It will come out to be 1. No, it's a very bad design. I cannot use this to generate a VREF circuit. Somebody said, okay, don't use resistor, use active load. Try to use active load. Let us try that. So I generate an active load ladder. It's an active load. It's like putting 3 loads in series. And let me say V2 is my reference or V1 is my reference. Anyway. And here is your VDD. You can generate in any way, this way or that. 3 different ways. Using 2 NMOSs, using 1 PMOS, 1 NMOS. Again compute the sensitivity for V reference. Either here or here or here. Again compute. Can you compute? Try to compute the resistivity. Assume all 3 devices are matched. Yes, Akash. Kindly do it and tell me the result.
Yes, ma'am.
What will be the sensitivity parameter? Write the expression for VREF. VREF, look here, it will be nothing but VGS of 1. Rather, I won't say it is even VGS of 1. It would be nothing but like putting a 1 by GM here and 1 by GM here. It's 1 by GM, 1 resistor here, 1 resistor here. Or you can, if you write VREF as VGS of 1, VGS of 1 is simply VDD minus VSG of 2. No? What is this VGS of 1? It is simply, what is this point? It is VDD minus VSG of 2. Now you substitute VSG. Now you substitute VSD differentiate, and then get the value for sensitivity. So you will again get a value of 1. Let me give it to you as a home task. And you take it as a take-home assignment. Do it and then convince yourself that it will come out to be again 1. So one thing I now know, that first of all, resistor ladder will not work. An active load ladder also will not work. Active load ladder will also not work. Something different I have to go for. Something different I have to think. So somebody proposed this structure, where you are having an R here and this kind of a structure. So Vref is again, it is VGS. Now look very carefully. Vref is nothing but VGS of the MOS. Only VGS. It's not VDD minus VGS. No, it is only VGS. It is only VGS. Vref is only VGS. So VGS, I know expression for VGS is known to me. Current through, it is in terms of current through MOS. So if this MOS is operating in a region of saturation, it would be VT plus under root of 2I. How much is I? I is VDD minus Vref by R. So VDD minus Vref by R and divide by mu and C of W by L, which I am calling it as beta. Clear? Yes, Apurva? And? Okay? So now we have got a Vref now. Deliberately we have written I in terms of VDD. Why? Because we want to look for sensitivity of Vref with respect to VDD. This is what I am interested in. Okay? And mu and C of W by L we are assuming they are all constants. So I am clubbing them together in the form of beta. So now we have got the expression for Vref. Now from here we try to get Vref. So this will give you a quadratic in Vref square. In Vref which you solve, you will get the expression for Vref. You will get the expression for Vref. Clear? So now, if I compute the sensitivity of Vref with respect to VDD, again I go by the definition VDD by Vref and differentiation of this expression with respect to VDD, which gives me this. Differentiate. Differentiate. And when I differentiate, and now suppose I design this circuitry for a certain current such that VDD is 10 volts, W by L is 10, R is 100K. Suppose I have designed this circuitry, so I know the values. So these values I put in over here. I put in over here. I substitute. VT is known to me. VT is known to me. Beta is mu and C ox. I know the mu and C ox. W by L is given. VDD is given. I put in all the values in this. I substitute. And the moment you substitute, it comes out to be 0.29. I am very glad. Now you are getting a value less than 1. That means this arrangement works. That means this arrangement suppresses the fluctuation. So my VDD may be fluctuating. Your Vref is not fluctuating that much. Fluctuations are less in the Vref. And once I know the values, I can also find out how much Vref I am going to get from this expression. Put in all the values, get the value for Vref. So two things you are getting: how much Vref you are generating, and what is the sensitivity of this Vref with respect to VDD. 29%, not 29. It is not 100%. It is reduced to only 29%. So if your Vref is changing by 100%. Then your Vref is changing only by 29%. Naturally, sizable reduction. I am happy. But still it is not close to 0. I would rather have very close 0.00029. I would be much happier to have this value. But this is certainly, it will work for me. I can make use of this concept. I can make that. So encouraged by this fact, now I experiment with BJT, I change my device. I change my device. I change my device. Let me say I have another device BJT. Again, I can put in a diode connection. So if I change my device, you may use NPN or PNP. Doesn't matter. Both should be diode connected. Again, you write expression. This is a diode current. This is a BJT current expression. I is equal to IS exponential VE by KT by Q. If it is a PNP, this will become V emitter base. Change the polarities accordingly. I have taken a PNP, it should be emitter base. If it is a PN, if NPN, this will become base emitter. Clear? So it would be IS exponential V emitter base by KT by Q. You are all aware of this equation. So now the same thing I do. My Vref will be V emitter base. So simply whatever is a Vref, so from here we try to get the expression for V emitter base. So V emitter base will be log of, natural log of I by IS multiplied by KT by Q. Multiplied by KT by Q. So this gives you KT by Q, natural log of I by IS. KT by Q is independent of VDD fluctuations. I am not talking temperature currently. I am taking one fluctuation at a time. So we are only looking at the effect of VDD fluctuating. Clear? So what is I? I is VCC minus Vref divided by R. It is this expression. And then you substitute this expression in this I. Then you substitute. You get somewhere around this. They are neglecting VBE, but you don't neglect. You get the exact expression. You try to get the exact expression. This is what you will get. Approximate. This is approximated result. Just to have an idea of, because otherwise you will have a Vref in the left hand side also and you have a Vref in the right. Maybe you can use a software to calculate that equation. Nobody says no. You can use MATLAB, write a program and then calculate that equation. But suppose I want to have an idea. First order estimate. So I assume that here VCC is much larger than V emitter base. VCC is at 10 volts, VB is only 0.7. Neglect it and then try to compute your sensitivity, which is coming out to be this expression. An approximated value I want to know with hand calculations. Okay, so when I do that, suppose my design is having a VCC of 10, R of 10, IS of 10 femtoamperes. I get my sensitivity as 0.0362. I get my, so even if you get a correct result, it would be somewhere close to this. I am further encouraged that now BJT gives you a better sensitivity parameter. Okay, now I try to find out why. BJT is giving you a better sensitivity. I look at my current expression. Look here, our Vref expression. In the Vref, look here, this VCC is coming within ln function or a log function. And log is a very slowly moving function. Log of 100 is only 2. Log of 1000 is only 3. So values are changing from 100 to 1000, but log values are only changing from 2 to 3. Very slowly moving function. Very slowly changing function. Similarly, look here. In my MOSFET, Vref depends on root of VDD. Root, square root. Square root is also a slowly changing function. Square root of 10 is 1. Square root of 100 is 2. No, 10. Square root of 100 is 10. So when values are changing from 10 to 1000, it's only changing from 1 to 10. But then it is fastly moving with respect to log function. So because BJT involves a log function, sensitivity, so your Vref is not changing that drastically. Even if VDD is changing drastically, Vref is not changing. So I am getting a better sensitivity in BJT than the sensitivity value in the MOSFET. But now I have got good methods of getting a sensitivity parameter less than 1. Now I am going to exploit these two expressions and design a circuit using these concepts such that I can ensure constancy of Vref or alternatively Iref. Understood? I think the period is over. So any query you have, Goa campus?
No, ma'am.
So your solution is, I will be putting up on Nalanda so that you can go through and you can, if you have any like things to be discussed or there's a discrepancy, please report to me. So when I start correcting your papers, I can address those issues. Okay? अरे दूसरी क्लास